Okay, welcome students. So, this is our next lecture on design of drop spillway. So, in this lecture we will be talking about the evaluation of uplift pressure and what is the condition of overturning, and all the things we will be solving by using a example problem. So, all these problems are connected with our past lectures. So, while solving these problems, you should remember or you should go through all the previous lectures what I have already told to you. Suppose we will be solving this problem, it is in continuation with the previous lecture of week 7 and lecture number 5. So, here the given length of apron is 4.5 meter, the drop is 2.5 meter, thickness of apron is 0.3 meter, depth of toe wall and depth of cut-off wall they are of 1.2 meter as you can see in this figure. The thickness of toe wall and cut-off wall both are of 0.35 meter, you can see in this figure. Assume that the downstream channel has been eroded to elevation of bottom of apron. That means, this channel has eroded up to the bottom of apron up to this line. So, that means, this shows that the tail water is up to this depth, that is equal to 3.5 meter in this slide. So, our question is that estimate the uplift pressure on base of the structure and draw the uplift pressure diagram for type B drainage with flow condition. So, before solving this type of problem, first you have to clearly visualize what is given in the problem. You can see this diagram, try to understand this diagram. It is full flow condition. So, full flow condition implies that there is water above the crest. So, here the water level is given as h equal to 0.75 meter and there is tail water. So, that means, at the downstream side you have tail water, so that it is full flow condition. So, you know that the uplift pressure is due to the soil pore pressure. That means, there is standing water and because of the standing water or submerged weight, the pore pressure generally develops and that is exerting pressure upward at the foundation material. So, for this we have to use the, as we have already discussed before, that for solving the uplift pressure we have to use the Lenz creep theory. The weighted creep length has to be estimated. So, that means, the uplift pressure is developed in this diagram, you can see along the line A, B, C, D, E, F, G, H and I. So, this is the contact surface between the structure and the pervious foundation material. So, because of the standing water on the upstream side as well as in the downstream side, the pore water pressure develops in this foundation material. That is why the pore pressure or the uplift pressure is created at these contact surfaces of the structure and the foundation material. So, once this is clear, then we can go for calculation of the uplift pressure. So, this is type B type of drainage with the full flow condition, and for that you have to estimate the y 2, the value of y 2. You can see in this figure the value of y 2. What is this value of y 2? This y 2 is nothing but it is the depth below the saturation water table. So, this y 2 depth is the depth or the submerged weight of this backfill material, which is computed just above the apron and the saturation line. So, this you can estimate from the table. We have already solved this type of problem in our previous classes. So, in this condition, from this table you can see for a high water table and relative permeability of foundation to backfill material equal, and type B drainage, for full flow condition we can estimate Y 2 equal to T plus S plus 0.15 F. So, here T is given 0.75, that is the depth of tailwater, S is 0.3 and F is 2.5 meter. So, we will get 1.425 meter. So, that means the height of this submerged backfill material from the top of this apron is 1.425 meter. So, by knowing this one, now we will go to our next step. So, in this step we have to identify the line of creep along the contact surface of the structure and foundation, which is along the line A, B, C, D, E, F, G, H and I. So, for solving you should understand the whole picture here. So, if you cannot understand this whole picture here, it will be difficult to estimate the uplift pressure. Okay. So, as shown in this figure, we have already estimated the what is the value Y 2, that is 1.425 meter. So, that is the depth of water table in backfill below saturation, and this is nothing but your submerged waste. So, that means pore water pressure is created in this fill material, which is up to a depth of Y 2, which is above the apron. This is above the apron. So, to get the value of H I, because we have taken our line of creep as A, B, C, D, E, F, G, H and I, and here our contact pressure or the uplift pressure generally develops here. Here generally our uplift pressure develops, which is vertically upward. So, along this line we have to estimate what is our pressure. So, at this point I, what is my water height? So, that is given by the depth H I. So, here H I you can see H I equal to 1.425, that is Y 2 plus the apron thickness of 0.3 meter. So, we will get H I equal to 1.725 meter, and you know that this is the water height. So, gamma W into H I, that is the specific weight of water into the water height, that is H I, you will get how much is your pore water pressure or the uplift pressure at point I. Similarly, we have to estimate how much is the water pressure above the point H, G, F, E, D, C, B and A. So, what will be the water height above point A? Here it will be equal to the tail water, that is 0.75 plus S, that is 0.3 plus my apron thickness, that is equal to 0.3. So, we will get H I equal to 1.35 meter. So, here the water pressure above point A will be H A, that is equal to 1.35 meter into gamma W, that is equal to 1000 kg per meter cube, that is the specific weight of water. And once these pressures are calculated at I and A, and from I to A along the line A, B, C, D, E, F, G, H, I. So, this is my contact surface, and there are horizontal lines or horizontal surfaces. The horizontal surfaces are I H, G F, then E D and C B. So, the horizontal lengths will be taken as 1/3 of that length. So, that will be the weighted length for these horizontal lines. You know this length creep theory. So, that is taken as 1/3 of the horizontal length, and the vertical or steep lengths are A B, C D, E F and G H, okay, and they will be taken as full. So, by using this concept we can now go for our next calculation. The second step is that you have to estimate the hydrostatic pressure head at point A, that I have already told you. So, that equal to depth of tailwater above point A. So, that equal to T plus S plus apron thickness. So, that equal to 1.35 meter. So, this equal to 1.35 meter, and the hydrostatic pressure at point A, that is equal to P A, we can calculate as 1000 to 1.35, that equal to 1350 kg per meter square. Now, our next step is that the depth of water table above point I, that will be equal to y 2, this is my y 2 plus the apron thickness of 0.3. So, we will get 1.725 meter, and the hydrostatic pressure at point I will be equal to gamma W H I. So, that equal to 1000 into 1.725. So, you will get 1725 kg per meter square. So, you can see along this contact surface A, B, C, D, E, F, G, H, I, at point A we have the pressure of 1350 kg per meter square, and at point I we have a pressure of 1725 kg per meter square. So, once this pressure difference is there, so it is mostly the pressure is distributed proportionately as the weighted creep distance. So, we can estimate what is our weighted creep distance along the line A, B, C, D, E, F, G, H, R and I. So, by getting the weighted creep distance, I can estimate what is the pressure variation or incremental pressure per unit creep distance. So, my first calculation will be to estimate the weighted creep distance, that equal to L W. So, that equal to sigma L B plus 1/3 of L H. So, we can get L B, those are the strip lines or vertical distances. So, these are A B plus C D plus E F plus G H, and these values are 1.2, because all these depths are cut off wall, toe wall, both are of 1.2 meter. So, 1.2 into 4 you will get. So, that is equal to 4.8 meter, and 1/3 of the all the horizontal lengths. The horizontal lengths are B C, D, F G and H I, and these values are given as 0.35, 3.1, 0.35 and 0.5 as shown in this figure. Okay. So, we will get L W equal to 6.233 meter. So, that is my weighted creep distance. So, one important thing here is that the vertical distance are taken as a whole, and the 1/3 weight has been taken for the horizontal distances. Then compute the change in pressure per meter of weighted creep distance. So, for that we have to get delta P equal to P A minus P I divided by L W. So, we will be getting 60.1916 kg per meter square per meter, 60.16 kg per meter square per meter length of weighted creep distance. So, this is based on the assumption that the pressure between the points A and I vary in direct proportion to the weighted creep distance. So, if you want to estimate the pressure level or the pressure for a specific creep distance, then we have to multiply delta P with that weighted creep distance. Then we will get the pressure at in between points, that is B, C, D, E, F, G and H. Okay. Now, we will go for our next calculation. So, this shows that how the pressure varies in between the points B to H, okay, and then to get the total uplift pressure. So, first try to understand this table. The first column shows the points A, B, C, D, E, F, G, H and I. Second column shows the weighted creep distance between points. So, these are the lengths. A B equal to 1.2 meter, BC, that is the horizontal distance. So, in this case BC equal to 0.35. So, it will be weighted value will be divided by 3. So, you will get 0.117 meter. CD is a vertical distance. So, that is equal to 1.2 meter, and D is a horizontal distance. So, that is taken as weighted divided by 3. So, you will get 1.033 meter. Now, our third column shows that it is incremental pressure between points. So, we have the pressure at location A or at point A 1350, we have already estimated this one. Okay. So, my incremental is here delta P into column 2. So, that is 60.16 our delta P value that we estimated in the previous slide, into 1 point is our distance. So, we will get 72.19 kg per meter square. That means, this 72.19 kg per meter square is the incremental value on the value of P A. So, for getting P B, that is pressure at point B, you will get P A value plus the value, that is the incremental value estimated at column 3. So, you will get 1350 plus 72.19, that equal to 1422.19 kg per meter square. Similarly, at point C, we have the weighted creep distance that equal to 0.117 meter. So, the incremental value will be 7.02 meter 02 kg per meter square, and my pressure at point C will be P B value plus this incremental value of 7.02. So, we will be getting 1429.21. Okay. Similarly, you can calculate for point D. So, here for point D it is 1501.40, and for point E it is 1563.57 kg per meter square. Then the average pressure between the points will be estimated as average of P B and P C. It is in between the average pressure between B and C. So, that will equal to P B plus P C divided by 2. So, you will get 1425.70, because the B C is a horizontal distance. So, if the pressure, the point pressure changes at B and C, but still then the average, because it is a horizontal distance, the pressure will act uniformly along this horizontal line. So, that is why we can take average pressure. So, that equal to 1425.70. Similarly, P D E, so that equal to 1532.49. Now, the base area for B C per unit width of the structure, so that equal to 0.35 A B C. So, you can see the length of B C equal to 0.35. So, 1 meter is perpendicular to the plane of this paper. So, that is equal to 0.35 into 1. So, you will get 0.35 meter square. So, pressure into the area you will get the total force. So, here you will getting 499 kg, that is your uplift load for B C along the line B C. Similarly, you can calculate for line D E. So, here the base area is 3.1, you can see here 3.1, and uplift load will be this P D E 1532.49 into 3.1. So, we will get 4750.7. So, similarly, we can go for calculation of other points. The next slide shows our calculation for the points F, G, H and I. So, here you can see EF is your vertical line. So, it is 1.2 meter. Similarly, you can estimate our incremental pressure, that equal to 72.19 kg per meter square, and HF is estimated as 1635.76, that equal to HE plus column 3, and the average pressure is estimated as 1642.8 kg per meter square. AFG equal to 0.35, you can see here it is 0.35, and multiplication of this column 5 with 6 will get 575 kg, that is our uplift load. Similarly, for FG the weighted creep distance is 0.117 and here we will get incremental load as or incremental pressure as 7.02 kg per meter square. So, pressure at point G will be getting 1642.79. Similarly, for G H we are getting uplifted load as 860 and my average pressure as 1720, and finally, you can say H I, that the pressure at point I is 1725 kg per meter square, that we have already estimated before. So, total uplift load will be summation of all these F values. So, that is coming as 6684.7 kg. So, by knowing the pressure at different points, we can develop our pressure diagram, because that is our second question, second bit of the question. So, we can develop our pressure diagram. Sorry. So, this shows our uplift pressure diagram. You can see all these values have been computed. P A we have estimated 1350, P B 1422. So, here P A the length is 1350, okay. Then P B is 1422, P C 1429, P D 1501, P E 1564, P F 1636. P G is estimated 1643, P H 1715 and P I is 1725 kg per meter square. So, that means this length is this value is 1725 kg per meter square. Okay. So, by knowing these pressure values, we have developed our uplift pressure diagram. Now, our next problem will be to calculate whether the structure is safe against overturning or not. So, all these computations have been taken forward from the previous lectures. So, this is a problem which we have already solved in lecture 4 of week 7 similar way. In similar way you can solve it, and those pressure calculations or force calculations can be followed. Those type of pressure calculations, the same procedure we can follow also in this lectures, because we cannot repeat those things to save our time. So, now try to understand the problem. The equivalent fluid density for all the horizontal pressure forces on the given drop spillway equal to 805 kg per meter cube. If you remember in our lecture 4 of week 7, that we have estimated what is our horizontal pressure load. Then the whole pressure, horizontal pressure is converted into equivalent fluid pressures, which is having a weight density, specific weight density of 805 kg per meter cube. Okay. So, you have to correlate this problem with that class. Now, second is compute the contact pressure in the drop spillway with the spillway operating at design discharge capacity. Design discharge capacity means it is flowing full, the flow condition is full flow condition. Check if the structure is safe against overturning. You know that why the overturning occurs. The overturning occurs because of our horizontal pressure forces and the uplift pressure forces, which is acting upward, and that is countered by our vertical forces, and the vertical forces are because of the weights of water on the structure as well as the backfill material. Okay. So, by using this we have to estimate the bending moment or the moment along some reference axis that I will talk about here. Then you have to say whether the structure is safe against overturning or not. Here the given values of unit weight of dry backfill are gamma d that equal to 1050 kg per meter cube, unit weight of moist sand and gravel as 2000 kg per meter cube, and that of concrete is 2400 kg per meter cube, void ratio of backfill that equal to 0.3. 0.35. The first step is that identify the nature of forces. So, these are all the force diagram we have already done in our previous classes, how to estimate the different forces by using our pressure triangles. So, here you can see in this figure there are total 15 forces acting. Among these 15 forces, F1 is the equivalent horizontal pressure force. So, F1 is the equivalent horizontal pressure force which has to be estimated as we have done before in the previous lecture, that is lecture 4 of week 7. Then F2, so this F1 force, it is horizontal. So, it is a turning force, it is the moment is turning in nature. F2, that is your weight of concrete head wall. You can see F2 is our weight of concrete head wall. You know the concrete density and the area you can calculate for unit depth or unit width. So, that you can get volume. So, you can estimate what is the force. Then F3 is weight of concrete apron. F4 is the weight of concrete cut-off wall. This is our cut-off wall. F5 is for toe wall. F6 is for concrete end seal. F7 is weight of saturated sand, because in this condition, by if you will consider the drainage type B, you know that this is my water table. So, this soil will be saturated one. Okay. So, for this you have to estimate what is the value of y 2, here it is 1.425 meter. So, that is my F7. What is F8? F8 is the weight of moist sand. You can see this is weight of moist sand, because our water is here. So, water table is here. So, naturally this soil or backfill material will be moist sand. F9 is weight of water above crest. So, this is the weight of water above crest, because the water is flowing full, which is having a height of 0.75 meter. Then F10 is weight of tail water on apron. This is F10, because this is our tail water and this is our water pressure. Then F11 is weight of tail water on end seal, because some weight is also above the end seal. So, that is my F11. And F12, F13, F14 and F15, these are all applet pressure, just we have computed in our previous problem, and the pressure values are given already here, all the values are mentioned here. So, you can estimate what is the pressure forces. Now, next step is that you have to calculate what is the porosity, because the void ratio is given. So, porosity equal to E divided by 1 plus E, void ratio equal to 0.35. So, we will get 0.259, and the saturated weight, specific weight of sand and gravel will be equal to gamma S plus N gamma W, because up to level Y 2, you can see in this figure, up to level Y 2 our soil is saturated, and in the saturated soil how much water is there? So, the water is filled in the void spaces or the porous spaces, and porosity is 0.259, that is equal to 25.9%. So, that means 25.9% of the soil pores are having filled with water. So, we will be multiplying 0.259 with 1000, that is the specific weight of water 1000, plus gamma S is the that is the dry weight. So, that is 1050. So, you will get 1309 kg per meter cube. Now, you have to choose the reference axis for horizontal and vertical forces. So, in this figure you have to choose the reference axis. So, here I am taking this downstream location, this is the O, this is my reference point, because of these horizontal forces and these upward forces, the turning will occur along this point. Okay. So, that is why I have taken this O point as my, you can say, reference point, and I will be taking a reference line along this downstream edge, that is for your horizontal forces, because I have to compute the momentum. So, that is for my all these vertical forces. For all the vertical forces, this is my axis, reference axis, and for all the horizontal forces like F 1, my reference axis is the base of this apron. So, that the base of this apron. So, this point is taken as my reference point. Okay. So, now, then I will calculate all the distances along this line. Now, I have to fill up the table right now here. I have to estimate what is my force F 1, F 2, F 3, F 4, F 5, all these things, and what is the magnitude. You know that the force is equal to the pressure into the area of that pressure triangle. So, that is estimated as for F 1, because this is equivalent fluid pressure. So, it is half into 805 my gamma equivalent into 2.8 is the height of the that equivalent pressure. So, you can see from the previous figure. So, into the height again 2.8. So, that I am getting 1355.6, and the distance of center of gravity from reference axis is 1.233 meter. So, that is equal to 0.3. So, that is the base of the apron, the thickness of the apron, plus 2.8 is the height divided by 3, because the center of gravity will act at a distance 1/3 of the height from the base. So, the moment will be the magnitude into the distance. So, I am getting here 3891, that is my turning moment, because that is the horizontal force and it is causing turning moment. F 2 is for head wall, and here the magnitude will be equal to area into the weight density of the concrete, that is 2400. So, I am getting 1680, and the distance of center of gravity from reference axis is 3825, that you can estimate by looking at that figure, and the moment is 6426, which is restoring in nature, because this is the vertical force. Similarly, F 3, F 4, F 5, F 6, F 7 and F 8 all are vertical forces, and these are having the nature, that is your restoring in nature, because these are vertical forces, and these forces can be estimated similarly, which is gamma W or gamma, that is the density specific weight of concrete into the area of the pressure triangle. Okay. And this is the distance of the center of gravity. So, that you can follow the figure and you can compute all these distances, and you can do the calculations subsequently. Now, coming to the uplift pressure, similarly you can do for water above crest. For water above crest, that is F 9. So, the density is gamma W, that is equal to 1000 kg per meter cube, and this is my area 0.75 is the height of water into 0.55 is the distance or the that is the length of the apron on which this pressure is acting. So, that is we will get rectangular type of pressure diagram. So, in this case you will get F 9 as 412.5, and similarly this is restoring, F 10 is also restoring, F 11 that is tailwater above end sill, that is also restoring in nature, and all these uplift pressure, that is F 12 to F 15 all are turning in nature. So, that we have already estimated in our previous problem, and the moment values are given here, calculated like this. So, you can try on your own. Now, the resultant vertical force will be sigma b. So, that equal to sigma the vertical forces which is causing downward minus the summation of vertical forces which are upward. So, we will get as 6843.2 kg, and the resultant moment sigma m will be equal to restoring moment minus sigma turning moment. So, that is equal to 37428 minus 20285. So, that is equal to 17143 kg meter, that we have taken from the previous table. So, Z value will be getting sigma m divided by sigma b. So, that is equal to 2.505 meter. So, what is this Z value? If you remember, in the previous lecture we have already discussed. So, this figure, if you look at this figure, is a plan of base, and now we have taken O as here, not here, but here it is O, and my reference axis is downstream edge, and this is my centroid point. This is d by 2, that is equal to 4.5 meter, and here Z is equal to 2.505 meter, which is just exceeding the center point or the centroid axis from this reference axis. So, this is my 2.505 meter, but d by 2 equal to 2.25 meter, and this is my eccentricity, and all these vertical resultant vertical forces are acting at this location. So, this eccentricity is estimated as here in this figure, it is this whole distance is z, this is d by 2. So, E will be equal to z minus d by 2. So, that equal to z we have estimated as 2.505 and d is equal to 4.5. So, we are getting 0.255 meter. So, that is my eccentricity. Now, we know the formula, that is the pressure sigma v divided by A whole into 1 plus minus 6 E divided by D. So, if you will take plus symbol and put the values, you can get P equal to 19769.24 kg per meter square, and for 1 minus 6 E divided by D, you are getting 10,644.98 kg per meter square. So, all these values are positive values. Since these values are positive, here pressure P A or P B both are positive. So, the structure is safe against overturning, and all these vertical forces are acting here. So, if the overturning forces are acting here, they are not able to overturn this structure. So, this is the condition for overturning, so that our structure is safe against overturning. So, in this lecture we have estimated how to compute uplift pressure and what is the condition of overturning. For the overturning, what are the horizontal moments or the restoring the turning moments and the restoring moments. By equating those, we can estimate our eccentricity, and based on that we can estimate what is the whether our pressures are positive or negative. If it is the pressures are positive, then you can tell that the structure is safe against overturning. So, for all these when we are going for solving all these problems, first you have to know that how to first you have to understand the problem. That means, the pressure diagram is very much important, the force diagram is very much important, because based on the force diagram you can estimate what is my pressure, what is the area of these pressure triangles, then the force will be equal to area into the pressure. Okay. Then at what location the center, what is the location of center of gravity, so that you can estimate the moment of these pressure forces, then we can equate the moments. Okay. So, we are ending here. In our next lecture will be on specifically how to prevent from sliding or to design for sliding. Okay. Thank you.